define data type, and n here is the number of elements of the type. Okay, and to use that, we suggest when you combine for the defined b width and the n, it's better to be a number of integer powers of 2. That will be more efficient using the memory and also provide an efficient way to access the memory. Okay. So in the C level, C++ level, then you can use the attribute to specify the vector data type. And in the using the AAHLS, you use this one. Okay. Let's take this as an example. That's an array of 8 elements of integers. So here for these variables, you actually have 256 bits bus width. Okay, and it's a declare using the it's a string type of a data bus. Okay, and this string has 256 bits. And when you do the operation, for example, in this operation multiplication, you actually have 8 integer multiplier operate concurrently on the 8 elements of the vector. Okay, so that's how you use the vector data type. Yeah. Okay, that's one important thing is to use the vector data type. So these vectors actually will be a consecutive memory space that you have n elements and each have t data type bits. Okay, so it suggests that actually it's a requirement. Otherwise, you use the memory very inefficient. So that means the n times number of bit of t. You hope that you have the greatest power of a power of 2. Yeah. So to efficient to use the memory. Okay. Sometimes the data type times the n is not to the power of 2. That you can use these macros that when you declare the data type, you assign the alignment to the align to the greatest of a power of 2. Okay, that ensures that for the memory allocation, that will be aligned to the nature by position, so that the hardware can more efficiently process the data. So make sure that you do create the vector data type which meet the memory alignment. Okay, for the operation. Okay, for the operation, there's an example for the initialization. In here, you declare 4 elements of an integer and initialize, or you can initialize all elements, or you can initialize different value for each element. To access the vector, you use the normal array index min to access the element of the vector type. And in AAHLS, settings AAHLS, it provides the following operations. You can directly use it, so you will synthesize the parallel hardware for these operators. Okay, there's another example here. I especially mentioned this is for the FPGA, PCIe FPGA card that it allows 512-bit memory data bus. So when you access the memory, often the memory bandwidth is a bottleneck of the kernel functions. So you want to maximize the memory bandwidth so that you like to use the 512 bits data bus. So how do you instruct the compiler to use 512 bits of memory access? There are several ways. In here, I illustrate three methods. One way is it's an integer type. So for 112 bytes, you can have 16 integers. Okay. So you can use a hint using the n divided by 16 times 6. Yeah. So use this as a hint to tell the compiler you want to access 16 integer at a time. Yeah. So that implies you're going to use the memory bandwidth by 12. Okay. Another way is that's a standard C vector data type. Yeah. Or you can use the HLS written in this way. Yeah. So in here, this in this case it's very much like enroll 16. Yeah, because you're gonna to for each AI. Okay, so this is very much like enroll 16. That you have A and B array, and each operates 16 of them. Yeah, at one time. Yeah. However, in here, you don't need to put the enroll here. Yeah. Because you declare the A array is a vector data type here with 16 elements. Yeah. Okay, in here I briefly introduced the float and doubles. And float and double, there's a standard AAAHLS 753. However, in the HLS compiler, it doesn't implement the full spec of the, it's not fully compliant, simply to reduce the FPGA resource. And for the floating-point processor in the standard processor, that's fully IEEE 753 compliance. Okay, so in this case, there will have cases that your C program is actually running in the local host processor with the floating-point processor, which is fully compliant with the IEEE 753. However, when you use the HLS floating-point, that since it's not fully compliant, so there will be a difference or error, and the error is still will be promised when you do the following situation, especially when you do the iterative operations, and the running error will be accumulated. Yeah. So in that case, you will see the promising errors. Or sometimes the library function for all the sine, cosine, or natural science functions, that all the library function actually using the Taylor series expansion. So people may have a different function approximations. So you will see the difference. And I mentioned that the floating-point processor in the processor it's extended precision. Yeah, and so it's will be different from the HLS compiler. And sometimes there's a different way of constant propagation or folding effect, or handle some abnormal cases, handled in different ways. So all of those are the source of errors. Yeah. So you need to be aware where the error comes from, and then you need to judge whether this kind of error is acceptable. Yeah, in here I simply said that for floating point or doubles, it does introduce errors. And then as a designer, you need to make a judgment. And Xilinx provide the floating point operator library. Yeah, you can use this library. And this library is fully pipelined with II equal 1. Yeah. But it's configurable. Yeah. So depending on your resource requirement that you may adjust it. Yeah. Okay, next introduce the composite data type. So we use struct in the C programming a lot. So same as in AAHLS implementation, we will use the struct data type. And the struct, there are multiple elements inside, okay? And in here, for the struct, the usage of struct, you can use it for the internal or global variables. Another case, using the struct on the interface, and they have different behaviors. What I mean different behavior is the aggregation and disaggregation. So when the struct data type used for the internal variables is disaggregate by default. What I mean disaggregate is you separate each element as one data resources. For example, in here, so this is the data type. Then you have a short variable A, and 4 element of an array with that type of character. So when you use as an internal variables, it will disaggregate. That means you actually internally, when you write the code to access those elements, you still access with the standard C way, C programming. However, internally, in the resource allocation, it actually allocate each array. It allocate one array for each element of the structural members. In here, so it create one array for the short variable A, and variable B is an array of 4 elements. So for each element is separate into an array. So you have another 4 array corresponding to the 4 element of this array B, variable B. So that's disaggregation. Yeah. However, on the interface, when you use the struct on the interface, it's actually aggregate by default. Okay. If you don't aggregate them, like this example, if you separate them, then you will have a 4 set, or actually 5 sets of memory access control logic. That means they have 5 sets of address generation and the control signal. So that's the reason that for interface, you want to minimize the number of interface signals. So there will be aggregate. When I mean aggregate, that you actually combine all the elements into one. You increase the bit width of the array to accommodate every element of this struct. So for this example, so that's a variable A has a 16 bits, and you have a 4 element of a character. Okay, so the total is 48 bits. So when you aggregate them, that you actually create an interface with data width 48, and you access individual element of the structure by different bit width. However, for these things, you really don't care because for the generated RTL code, you use this way to access. But in the C level, you are not aware of this. Yeah. Okay. So, however, when you look at the after synthesis, you look at the interface port, you will find out that actually all of the element of the structure aggregate into one interface with a wider data bus. Okay, for struct of array, yeah, that's an aggregate, but yeah, that's, you already know that. Okay, in here, when you aggregate that, by default, okay, the data type by default is aligned on 4-byte boundary. Okay. So, but when you disaggregate that it will still create by alignment because if it's a 5-bit, for example, the element A has 5 bits. It's very difficult to access the data with arbitrary bit width. So minimum is a byte 8 bits. So when you disaggregate, you actually allocate the memory array with a minimum 8 bits. Okay. And in this example, that it's actually the aggregate, but by default it's aligned as a 4 byte. But this example is specified that it aligns as a 2-byte boundary. That means when you aggregate them, the final bit width will be 2-byte alignment. In this case, that you will pad in with 8-bit of zeros to make it 8-byte, 2-byte alignment. So when you do the aggregate or disaggregation, you should be aware that there is a bit padding and alignment happen here. Okay, here, that's in C data type, people often use the enumerated data type. It's simply a nice coding style to make the code more readable. Okay, so it defines the variable element of the variable in a more readable way using the Markov definition. Yeah, so this one actually doesn't have a much HLS semantics here. Yeah. And for the union, okay, union is people use the union to, how to say, disassemble a data type so that you can access partial of the variables easier. For example, you can define a union with, for example, struct integer A and B. Okay, that's maybe variable A. And also you can have a double a variable B. Okay, so actually this data type is 64-bit. 64-bit. Actually, it's a 64-bit data type. If you want to access partial of the storage, in this case, actually, it's alias into 2 integer 32-bit. Okay, so you can access 64-bit as a whole through the variable B, or you can access this storage with 2 independent 32-bit data. Yeah. So that's the usage of a union. However, there are some restrictions on the use of unions. Yeah, here in these cases. Yeah. Okay. Next, I will introduce a different type of qualifiers. First is volatile. Volatile is used very much in the embedded programming. And embedded programming, it deals with the hardware. And to access the hardware, you don't want the compiler do too much optimization. For example, you want to access memory map I/O control registers, and you actually access the address multiple times. Yeah, and today's smart compiler may, for example, read. Okay, you read the same address multiple times. Compiler is so smart that think they will reduce only one read. Okay, and the read has a side effect on the I/O device. If it's reading on the memory, there's no problem. You can reduce it. Yeah. However, when you read the I/O device, each read has a side effect. For example, the hardware is implemented with read clear. The hardware, for example, hardware, they define the register and the type says read clear. That means when you read that register, after read, you will clear its contents. And it's often used, for example, like the interrupt status register. Okay, when you read the interrupt status that you want to clear the register B, and the interrupt line will be deasserted. Otherwise, the software have to do a explicitly write clear operation, and that's an overhead for the software. Okay. So that's the case. For this kind of assets, embedded programming use the volatile oftenly. Okay. So volatile, this type of qualifier, basically tell the compiler don't optimize it. Okay. So it also means no burst access, no port widening, and no decode elimination. The compiler, those things are often done by the compiler. Yeah. And simply tell the compiler don't do any optimization. Yeah. And static, we often use static. Basically, you allocate local storage. Okay. So that it can hold the value between function call and create registers. Yeah. And when we write the software, there's a so-called reentrant software. Okay, and that means that function has been called by multiple processes. Yeah, and if the code is a reentrant, that's every time when you call this function, it will initialize its internal memory or internal variables. And when you create the static on a certain variables, that means when you call the function, don't initialize that variable to 0. Okay, so that it can hold the value between the hardware code. And that's match the hardware behavior, because for hardware, for each hardware or function it creates, it has it's a dedicated hardware resource. And that hardware resource, you want to keep its value instead of every time you call it that the internal storage get reinitialized. Okay, so this tool we often use in the AAHLS. And for the constant, it's important that the compiler can do the optimization for you. So that it knows that it's a constant, so you will do the constant propagation. And by doing this, the synthesis tool can eliminate unnecessary hardware. Another is a global variable. Global variable doesn't create the I/O ports on the RTL interface. Okay. Next, I will introduce the pointer. Yeah. We know in C language, people use the pointer a lot and use a very also the erratic way. It's people use it so freely and create a lot of trouble for the AAHLS compiler tools. So it has in order, because the pointer can point to any kind of type, and pointer can be casting, can be, yeah, it just point to a location. But for hardware, it's not just a location. It needs to know it's a resource for this object. Yeah. So if the pointer can arbitrarily point to any object. Because for pointer, just 32-bit or 64-bit integer numbers. Yeah. However, the object behind that, the address, actually represents certain hardware. So that has to be known during the compilation stage. So that's why it imposed several rules or restriction on the use of a pointer. Okay. The first thing is we often use the multiple access pointer create inefficient bus interface. But for each pointer access, it's actually it's a individual access. So if a pointer to a memory, that will be a single access memory address, then it will be very inefficient. So it's better use a streaming of FIFO. If you use a streaming of FIFO, it knows it's a sequential access so that it can do the burst access. That will be much more efficient. Yeah. And for array of pointer, it limits to that pointer only point to a scalar or point to an array, but it must be a scalar array. Yeah. And the pointer casting, as I mentioned, that they're only limited to between the standard C++ data type. Okay, in the next, I will introduce several the use of pointers. And for this case, you have two array allocated, and you can use the pointer point to multiple objects. Depending on, in this example, depending on the select, the pointer can point to A array or B array. And this this design is okay. Okay, for pointer to pointer, actually, it does not support on the top level interface. If you have to use the pointer to pointer on the top level interface, like for example in this case, you actually use the pointer to the object. For any of the in here, if you look at here, this is a flag. The pointer flag is actually is a pointer to data T, and you call this function with another pointer. So for this function, it's a pointer to pointer type. Okay, so pointer to pointer cannot appear on the top level function. It can be a sub function. If it's a sub function, that the AAHLS will inline all the function using pointer to pointer. So it will automatically inline this function, so that internally you won't have a pointer to pointer access. Okay, this is an example of array of pointer, and this type actually commonly used. So basically, in this example, you have a two-dimensional array, A, N, 10. Okay, and then you create another pointer array. This actually is a pointer array. Okay, so that's a pointer AN. Okay, for each element, you point to a row of the A array in this code here. Okay, you have the entry for pointer A array and point to the element 0 over each row. Okay, and then you can do the operation to copy the B array, two-dimensional array, copy to this B array. Yeah. So this example simply show you the use of how to use the array of pointers, and this code is okay for AAHLS because the pointer is point to an array of scalar. Okay, so this case is okay. Okay, and pointer casting, yeah, it's only available for native C++ types. Yeah, in this case, the data T and D integer T are standard C++ type. So in this example, for the integer, you have actually that's a integer type, and for each of them is a character. Okay, for an integer type, and you want to process each byte, then you need to do some kind of casting. Yeah. In this example, the pointer actually is a point to a character. Yeah. So for this A array, actually the A is an array of an integer, and you point to one entry of the integer, one element is an integer, and then you can process it because you're casting into a character data type, then you can process each byte of them. In this particular example, you want to add this 4 bytes together. Okay, so given an integer with 4 bytes, and you want to add individual bytes, yeah, that's how you do that. Yeah. Okay. Okay, for pointer on the interface, basically it's synthesized to simple while or handshake. Okay, and the pointer on the interface is only read or written once per function call. Yeah. So in this example, it will read the D and then write the D variables. Yeah. So when you call the function that you perform this pointer read or write only once. Yeah. However, for this code, okay, that's a pointer arithmetic. People like to do some arithmetic operation on the pointer. Then it create a lot of troubles. In this example, you can see it does the that's a pointer to an array, and you try to accumulate the value of this array. However, it starts from the second value. Okay, and when you start from a second value, it does not constitute that it is a sequential access, because when we say a sequential access, we mean the starting from 0 and then increment the address, sequentially access incrementally. So for the original pointer type, you only create the protocol. The interface is either while, handshake, or FIFO. And for those type of interface, it could not access out of order because there is no address information on the interface. Yeah. And in this particular example, you start access from the second value. Okay, so you need some kind of indexing or addressing scheme in order to access the proper element from the arrays. Okay, so for data as out of order, then you need a data as indexing scheme. That means you need to have an address. In this case, you have to use the array. Okay, so for this code, the HLS could not synthesize the design properly. Yeah, you have to change to the array, and then in an array, then you can use the index. Index is actually the address of the memory. Yeah. So if the code has a pointer arithmetic, then it needs an address to access the array. Then you need to use the array on the interface instead of using the pointer. Okay, here, there's a multi-access pointer on the interface. Okay. So for this case, so using the pointer access multiple times can introduce unexpected behavior after synthesis. So for the multiple access pointer, it's better to use the string interface. Yeah, and for use the string interface that for if you don't use the string interface, okay, then you have to declare it's a volatile. Volatile means that the compiler don't do any optimization from the compiler. For this kind of access compiler, if you don't declare volatile, then the full read of the D array will be reduced to 1. So they will be reduced to 1 read on DI. And you have a 2 write on the DO. So it will reduce to 1 write on DO. Okay. So in this case, we need to put the volatile here. Okay. And even though with these settings that when you do the code simulation, you may still run into problem. Yeah. Because when you call, imagine here, when you call these functions, they actually read the full data from the DIN array. Okay. So when you declare the interface, you need to make sure that you declare this FIFO interface, AP FIFO, and then you have to set the FIFO depth at least 4. Otherwise, the C simulation and the hardware coding will be different. Yeah. Okay, so there's a lot of nitty-gritty things to deal with multiple access pointer. So it's better to avoid this kind of coding style. Yes. No. In this design, it actually, as I said, it reads the same address multiple times, right? Yeah. If the D is I/O, since it's I/O and you copy to the local, the behavior is different. So let's say the DI is a memory map I/O. So that means every read has its side effect. So you copy over to local and you read the local variable 4 times. But for that memory map I/O, you only read once. So the system effect will be different. Yeah, so you have to fully respect all the I/O transactions. Yeah, because it has the side effect. Uh, mm. Say it again. Mm-hmm. Oh, let's say we don't know the background of this code. Okay, I can imagine one use case that that memory location, okay, point to a location, memory location, and that memory location, let's say, is a memory map I/O. So it actually is an I/O device. Okay, and let's say that the I/O device is the interrupt status or message interrupt. So probably you don't know the message interrupt. Okay, so let's say that device using a memory address to tell you certain information. Okay, let's suppose on the device side is implement a FIFO. Okay, every time he wants to send you full message. So you have to read 4 times from the I/O, so that you cannot copy over and read the local. You have to go on to that device, read 4 times from its FIFO. Yeah, because in here, you don't know the background of this code. Yeah, I just try to imagine you write this code, the D actually is a message queue, let's say, on the IO side. And that IO device want to send you phone message. Okay, but same address. It's the same address like here, the same address. Yeah, so you want to read 4 times. So you cannot reduce, say, just read 1 time. Yeah, you have to actually read 4 times to get the full message back. Yeah, yeah. So I understand that you probably didn't do the embedded programming. So it's hard to imagine this usage, but it's very open. When you do the embedded system, that's a very standard way to communicate with the I/O device. Yeah. Mm-hmm.